Welcome to the Explainer. Today, we're going to dive into a fundamental tension that's really at the heart of all AI. It's this constant tug of war, that decides whether a model is going to be a brilliant predictor or just a spectacular failure.
While the answer, it turns out, lies in this really delicate balancing act. See, every single AI model out there is struggling with two competing types of error. And that conflict, that's what we call the bias-variance dilemma. All right, let's dive into the predictor's dilemma. We'll start with the most basic challenge, right? How in the world do we teach an algorithm to look at the past so it can make really accurate predictions about the future? You see, the goal here is to get our model to pick up on the true signal, the real patterns that are hiding in the data, without getting fooled by all the random noise. And if we can pull that off, the model will generalize well. That's just a fancy way of saying it'll work on new, fresh data it's never seen before. And trust me, that is the absolute holy grail of machine learning. So let's meet the two faces of error. This brings us right to those two opposing forces that really every data scientist and machine learning engineer has to deal with constantly: bias and variance. So you've got bias, the oversimplifier, and variance, the overreactor. The best way to think about them is like two kind of extreme personalities. On one side, you've got bias. This happens when a model just makes way too simple assumptions about the data. But on the other side, you've got variance. This is from a model that's just way too sensitive. It basically overreacts to everything in the training data. Okay, let's break down bias first. A model with high bias is kind of like a stubborn predictor. It's got this super simple, rigid view of the world, and it just completely ignores the more complex, nuanced patterns in the data. This leads to a big problem we call underfitting, which basically means the model just isn't smart enough for the job. And then there's variance. A high variance model is the complete opposite. It's nervous and erratic. It pays way too much attention to every single little data point, and that includes all the random noise. So what happens? It ends up just memorizing the training data instead of actually learning the real pattern underneath. And we call this one overfitting. To make this crystal clear, nothing beats a good old bullseye analogy. So, look at this target. This shows a model with high bias, but low variance. See how all the shots are clumped together? But they're way off the mark. The model is consistently wrong, sure, but it's wrong in the exact same way every single time. Okay, now check this out. This target shows the exact opposite problem: low bias, but high variance. The predictions are just all over the place, right? They're totally imprecise. But, and this is the interesting part, if you were to average all those shots out, their center is smack dab on the bullseye. So the model isn't consistently wrong in one direction, but its predictions are just totally unreliable and wildly different each time. And this is the goal, the target on the right. This is what a model with both low bias and low variance looks like. The predictions are accurate, they're precise, and they're consistent. We are hitting the bullseye time and time again. So that brings us to the balancing act. I mean, if the goal is obviously low bias and low variance, you might be wondering, why is this so hard, right? Why can't we just tune a model to have both? Well, it's because, and this is absolutely crucial, they are in direct conflict with each other. Take a look at this U-shaped curve. As you make a model more complex, which is that line across the bottom, the bias, that's the red line, it goes down. Great. But at the exact same time, the variance, the blue line, shoots up. This push and pull is what creates that classic U-shaped curve for the total error. And our sweet spot, the best possible model we can get, is right there at the very bottom of that U, where that total error is as low as it can be. Let's make this a little more real with an example. So, imagine all these blue crosses you see are our data points, okay? And that smooth red line, that represents the true pattern that's hidden in the data. That's the signal we want our AI to find. Okay, so what happens if we use a really simple model? Well, we get something that looks like this. This is high bias in action, folks. The model is just too simple. It can't capture that important dip right there in the middle of the data. It completely misses the real pattern. It underfits. But look what happens when we go way too far in the other direction and use a super complex model. Now this is high variance. See how the line twists and turns like crazy just to hit every single blue cross? It's basically memorizing all the random noise from our training data. A model like this, it would be absolutely useless for making predictions on any new data. It's a classic case of overfitting. And this brings us to the most important takeaway, really. Getting a perfect fit on your training data, it's a trap. The real goal is to find that sweet spot, that optimal model complexity. It's a model that actually accepts a little bit of error from both bias and variance, because that's what's going to give you the best possible performance out there in the real world. All right, so how do we tame these errors? This is obviously a huge challenge. So how do the pros, the practitioners, actually manage this whole balancing act in their day-to-day work? Well, they've got a whole toolbox of methods at their disposal. For instance, there's a technique called regularization. You can think of it like putting a leash on a really complex model. It intentionally simplifies the model just a tiny bit, so it adds a little bias on purpose to stop its variance from spiraling out of control. Then you have other cool strategies like bagging and boosting. These are called ensemble methods. And the idea here is you combine the predictions from a bunch of different models, and by averaging out all their individual mistakes, you end up with a final answer that's way more robust and accurate. But what's really fascinating is that this trade-off, it's not just some technical problem for algorithms. It's a surprisingly human one. It's a dilemma that you and I, we all navigate in our own decision-making every single day. In fact, researchers like Gigerenzer and Brayton have argued that our own brains, they often default to high bias, low variance strategies just to get by in the world. We know these better as mental shortcuts or heuristics. I mean, just think about it for a second. Our life experience is actually a pretty small training set, right? So instead of trying to build some super complex, high variance model for every single new situation we face, what do? We fall back on simple, robust rules of thumb. Now, these rules, they might not be perfectly accurate 100% of the time. That's the bias. But they are consistent and they help us generalize surprisingly well. So, this leaves us with a pretty fascinating final thought. The next time you have to make a snap judgment or you decide to just rely on a gut feeling, ask yourself this. Are you just performing your own deeply human version of the bias-variance trade-off? Are you choosing the simplicity of a reliable rule over a perfectly calculated but maybe unstable analysis?